Welcome to the lecture in Approximation Algorithms. Today we're going to talk about greedy algorithms and local search. My name is Rasmus Pagh. Today we're going to look at 4 case studies exemplifying greedy approaches and local search. Scheduling overdue jobs, the case center problem, scheduling jobs in parallel, and finally the metric traveling salesperson problem. 3 of these will exemplify greedy and the last one local search. Let's define the problem of scheduling overdue jobs. The input consists of n jobs. Job I takes time pi to complete. So this is job 1, 2, and 3. Job I has a release time Ri, which is the earliest time it can start. This is not negative. And finally, di is the amount of time left for job I. di is less than or equal to 0 because all the jobs are overdue. So we need to find a time to schedule each job, and these should be non-overlapping. So for example, we could do like this, and we would get a cost of C3 minus D3, where C3 is the completion time of job 3. So the objective that we want to optimize is to create a schedule with no overlapping jobs that minimizes the maximum lateness. So that is, minimizes the maximum over I of Ci minus Di, where Ci is the completion time of job number I. There's a natural greedy heuristic that we can employ. At time t, we consider all the unscheduled jobs that have release time greater than or equal to t and schedule the one with the earliest due time Di. So for example, suppose these are the jobs, and this is time 0, and we have initially allocated each job at its release time. Of course, this is an overlapping schedule, so this is not yet valid. So we can move these back and forth. So what we do is that we look at the release times, and suppose that R1 and R3 are both due. Then we take R3 first, because it has the earliest due date. Then we schedule R1 because it has the due date which is later, and finally R2. The cost in this case becomes the time that R2 is finished minus D2. So notice here that because the jobs are running without any idle time, we can express the time where job 2 finishes as the starting time for job 3, which is the time where we started processing the jobs, plus the sum of the processing times for P1, P2, and P3. So this is the ending time of job 2, from which we subtract D2. Before moving on with the analysis, I'd like you to pause and think. Try to find an input W with 2 jobs where greedy's schedule has cost at least 1.99 times the optimal. Let's consider the analysis of the greedy algorithm. Consider the last job scheduled. Let's say job J, it stops at time Cj. So when does it start? Well, obviously at time Cj minus the processing time Pj. Maybe this is equal to Rj. But in general, it could be that there was some other job that was running at time Rj. In that case, this other job, let's say call it J prime, stopped at Cj prime and started at Cj prime minus its processing time. And in general, there could be like a sequence of jobs where each one was waiting for the former one to continue. But at some point, there's going to be a job that actually started without any running job, and that job had to start at its release time. So let's call this job a set of jobs S. Then we can write Cj as the minimum release time in this set, plus the sum of all the processing times in S. So the cost of greedy, in other words, is Cj minus Dj, which we can express as using this formula. So let's move this a little bit. So now we would like to upper bound this cost. So first consider the 2 first terms. so the minimum of the RJ's release times plus the sum of all the processing times. I claim that this is less than or equal to the completion time for any schedule. In particular, this is less than or equal to opt. Similarly, minus dj is less than or equal to opt. And in total, this is less than 2 times opt. So for any valid schedule, in the set of jobs, there's going to be S of jobs. There's going to be one that finishes last. And there's no way that we can schedule the jobs in a non-overlapping way, in such a way that it completes earlier than the earliest release time plus the sum of the durations of the jobs. Similarly, even if we complete all the jobs by time 0, we are going to get a cost that is at least minus dj for every j. And by what we saw before, the constant 2 is tight. In the k-center problem, we are given a set of points P, and we want to cover it with k disks of radius r, where r is as small as possible. The center of each disk should be a point in P. So for example, in this example, with k equals to 3, we could consider these 3 centers. We need to define the distance from a point x to a point set S. It's defined as the minimum distance from x to y, where y ranges over the points in S. With this definition, the objective of the k-center problem is to choose a set S, which is a subset of P, such that S has k points, and the maximum distance from x to S is minimized where x ranges over the point in P. A natural greedy algorithm for the k-center problem consists of building the set S point by point. We start with S equal to the empty set and add at each step a point x that is responsible for maximizing the distance to S. So in other words, in each step we add the point x such that the distance from x to the current S is maximized. And we repeat this until we have a set of size k. So in the example, initially all the distances are infinity, so we can start with any point. So let's choose the one shown here in red. The next one we choose is the one furthest away from the point in red. And finally, we are going to choose the point at the bottom, which is the one that is furthest away from the 2 points that we already chose. And we can draw disks of radius that is sufficient to capture all the points, and that gives the greedy solution. At this point, I want you to pause and think. I want you to argue that greedy can sometimes return a k-center that is 2 times the radius of the optimal k-center solution. Let's analyze the performance of the greedy algorithm for k-center. Let's consider an arbitrary optimal solution. Of course, we don't know what that is, but we can imagine it, and we can try to compare the cost of the greedy solution to it. So the optimal solution will consist of k-centers and disks of radius r around each center that contain all points. There are 2 cases. First of all, if greedy selects a point from each cluster, I claim that we are done. Why is that? Well, no matter what we choose from each cluster, the maximum distance within a cluster is at most 2r. So in particular, every point is within 2r of one of the points selected. The other case is that greedy does not select a point from each cluster. So there must be some cluster from which greedy selects at least 2 points. Let's suppose the 2 points are chosen in this cluster as part of the greedy algorithm. What does that mean? It means that 2 points are chosen that have distance at most 2r, which means that all the points in P must have distance at most 2r to a point in S, and we are done. We next consider the problem of scheduling jobs in parallel. The input consists of a number of jobs, let's say n jobs, that have different processing times p1 through pn, and we need to allocate these jobs to m machines. So for example, we could allocate the jobs like this, and that would give a certain make span, which is the maximum processing time for any machine. The objective is to allocate jobs to machines to minimize the maximum make span. So the local search approach to solving this problem is to start with any feasible solution. For example, assign all jobs to one machine. Then we repeat a local change, in this case move one job to another machine in order to improve make span, until it's no longer possible to improve by making a local change. Let's consider an example. Suppose we have a configuration of jobs in the local search like this. Then it's possible to move one job, the first job from machine 1, to the last machine, which will reduce the make span. So local search does these kind of changes until it terminates. Now it's time to pause and think. I wanted to show that local search may not necessarily find the optimal solution. How large a gap can you get? Let us analyze the local search algorithm. Let C* be the cost of an optimal schedule. It's easy to see that C* cannot be too small. In particular, it has to be at least the average cost over all m machines, the sum of all the pi's divided by m, simply because the worst case cannot be smaller than the average. Now suppose that the local search returns a solution of cost more than 2 times C*. So we have the m machines, we have the average cost, and C*, which is greater than or equal to the average cost. There has to be at least one machine, for example M1, where the cost is less than average. Let's suppose that the largest make span is in machine MM. The last job schedule on MM needs to have started before the average cost. Why is that? Well, that's because otherwise the local search method would have moved it. Also, the last job needs to have cost or length at least C*. Why is that? Well, we assumed that the local search returned a solution of cost at least 2 C*, and the last job started before time C*. So let's denote the length of the last job by Pj. What can we say about the make span? Well, it is at most equal to the start time of job j plus the processing time Pj. The start time is at most the average processing time by the local search property plus Pj, and both of these are upper bounded by C*. So in total, it's at most 2 C*. The final problem we're going to look at today is the metric traveling salesperson problem. We're given a point set P and a metric on these points. Let's call the distance from point I to point J Cij. And the goal is to find the shortest tour of all the points. So something like this, like a closed tour. So we want to minimize the sum of all the edges in the tour of Cij. There are 2 observations we can make. First one is that a tour includes a spanning tree. So we can simply omit one point or one edge from the tour, and we get a very special spanning tree. It's a path, in fact. The second observation is, at least if the number of points is even, a tour is going to consist of 2 matchings on the points. So let's color the edges. So all the red edges here make up a matching, and all the yellow edges make up a matching. So this means that an optimal tour has weight at least 2 times the weight of a minimum weight matching, and also an optimal tour has weight at least the minimum weight of a spanning tree. So if we could somehow add a minimum weight matching and a spanning tree, we would get a 3/2 approximation. This is the idea behind Christofides' algorithm, which was described the first time in 1976. It consists of 2 phases. In the first phase, we compute a minimum spanning tree, T, of the graph. In the second step, we look at the odd degree vertices in the minimum spanning tree, so the leaves and all internal nodes that have odd degree, and compute a minimum weight matching on those. So let's call that M. So for example, the minimum spanning tree could look something like this. And let's mark the odd degree nodes in orange. So it consists of some leaves and some internal nodes. And consider a minimum weight matching on it. So for example, it might consist of these edges. So note here that there might be parallel edges that exist both in the matching and in the minimum spanning tree. So now I claim that we can use these edges to construct a tour. And the tour will have weight that is bounded by the weight of the minimum spanning tree and the weight of the matching. So how do we do this? Well, we use a greedy approach. So we start anywhere and we just choose edges that we haven't used yet. And I claim that this process is never going to get stuck. So there's always going to be a choice we can make until we get back to where we started. In this case, we are done now, but in general it might be that we need to do this several times to form several tours which we can then link together. However, we might have visited some nodes several times, but that's no problem because we can make shortcuts. So whenever there's a node that we visit twice, we actually get a better solution by the triangle inequality by going directly to the next node that we haven't visited. So introducing these shortcuts, and this is where we use that we have a metric, we get a tour that visits each node exactly once. Finally, we need to bound the cost of the tour. It's bounded by the cost of the minimum spanning tree, whose edges we have included, plus the weight of the maximum matching. By the argument on the previous slide, the former is bounded by the optimal tour weight, and the latter is bounded by 1/2 times the optimal tour length. This was the best known until very recently, but in 2020, Carlin, Klein, and Garan showed that it's possible to improve the approximation factor of 3/2. So specifically, they get an approximation factor which is smaller than 3/2 by some epsilon, which is greater than 10 to the minus 36. So a tiny improvement, but it shows that 3/2 is not the best. Welcome to Approximation Algorithms and the lecture on rounding data and dynamic programming. My name is Rasmus Pagh. Today we are going to talk about rounding problems to make them feasible. We're going to look at 2 case studies, scheduling parallel jobs, where we go from a 2 approximation to a 1 plus epsilon approximation, and bin packing. First, let's recall the problem that we considered last time. We want to schedule jobs of different durations P1 through Pn, all non-negative, on M machines. The goal is to optimize the make span, that is the total time to finish all jobs. Last time we looked at a local search algorithm and showed that it gave a 2 approximation. Today, instead, we are going to look at a different approach, a greedy approach that works by processing the longest jobs first. Without loss of generality, we can assume that P1 is the longest, P2 the second longest, and so on. So any feasible solution has some job that finishes last. So in general, a schedule could look something like this, and let's say it's M2 that finishes last, and let's call that last job J, and it has processing time Pj. It's easy to see that when job J started, all machines must have been busy. Why? Well, because otherwise job J would have been started earlier. So there can be no idle time before this. What do we know about the period in which there's no idle time? Well, it's at least the average processing time, sum of Pi over M, which is a lower bound on opt, as we saw last time. So if Pj is less than epsilon times opt, we actually have already an 1 plus epsilon approximation. So somehow short jobs are easier. We're going to define T as the average processing time and split the jobs into the easy ones and the difficult ones. So in particular, the ones that have processing time less than T over K for some parameter K, we call them short, and the ones that have longer processing time we call long. And K we're going to choose as something like 1 over epsilon. Now I'd like you to pause and think. Why is it that there can be at most M times K long jobs? And secondly, how many ways can we schedule the set of long jobs? Now the algorithmic idea is to first handle the difficult part of the problem, the long jobs. We first schedule the long jobs either optimally or at least nearly so. Then we schedule the short jobs in descending order with the greedy mechanism. There are two cases to consider. First of all, if the last job to finish is short, I claim that we're done. Why is that? Well, the cost is at most optimum plus the length of the shortest job, which by definition was optimum over K at most, because of the lower bound on opt. The other case, the last job to finish is long. Then the cost is actually the same as if there were no short jobs at all. So it must equal opt, and we're done. To implement this algorithm, we need to consider all possible ways of scheduling the long jobs. This gives a running time of something like O of M to the Km, which is a bound on the number of configurations of the long jobs. The question is, can we do better when M is large? We are going to show that the answer is yes. To this end, we redefine T. So now T is simply an upper bound that we assume is known on opt. And the goal now is to find a schedule with makespan at most 1 plus 1 over K times T. So if T is a reasonably tight upper bound, that gives us an approximation algorithm. So now short jobs are defined with respect to T as before. To get better running time, we are going to round. So we are going to round Pi down to the nearest multiple of T over K squared. So this means that there is at most K squared possible lengths, because we know that all jobs have length at most T, since T is an upper bound on opt. And now we claim that we can find a schedule for the long jobs using dynamic programming. How do we do this? There are a couple of observations. First of all, there can be at most k jobs per machine in a schedule of length at most t. That's because all the jobs are long, without loss of generality. Since there are only k squared possible job lengths, an arbitrary input to the problem can be described by a vector of length k squared, saying how many jobs there are of each length. We define opt n1 through n k squared as the smallest number of machines needed to execute a workload with max make span at most t. Such an optimal schedule must consist of assigning jobs to one machine in some way and then assigning jobs optimally to the others. In other words, its value is equal to 1 plus the minimum over all ways of assigning jobs to one machine of the opt of the job that remains after assigning to one machine. So this gives a recurrence that we can use for dynamic programming. And we can compute this bottom up by looking at the sum of the ni. So first compute all inputs with 0 elements, 1 element, and so on up to. And at some point we are going to reach the opt for the true input configuration, and we are done. So the final thing we need to discuss is how to find t. T needs to be an upper bound on opt, but it needs to be pretty close. So one easy solution is just to try t equals to 1 through 2, 3, and so on. There's a smarter choice, which is described in the book. So what do we end up with? Well, the final algorithm runs in time n to f of k, where k determines the approximation quality. And we can make the approximation arbitrarily good, arbitrarily close to 1 by increasing k. So this means that we have a so-called polynomial time approximation scheme. However, the time does grow exponentially with the choice of epsilon if we want approximation factor 1 plus epsilon. Later in the course, we are going to see fully polynomial time approximation schemes, where the running time depends polynomially on n as well as 1 over epsilon. In the next part of the lecture, we are going to look at the bin packing problem. In this problem, the input is a set of numbers in the range 0 to 1. And the objective is to choose an assignment of the indices 1 through n. So that is, assign these numbers to m bins, such that m is minimized and such that in each bin the elements sum to a number less than or equal to 1. As it's phrased, it's actually hard to find a good approximation algorithm. It's NP hard to distinguish the two cases where it's possible to pack all the items into exactly 2 bins of weight 1, and the case where you need 3 bins. This means that a 3/2 approximation is the best we could hope to get unless p equals np. But actually we can almost get an approximation scheme in the following sense. So for every epsilon larger than 0, we can pack into a number of bins, which is 1 plus epsilon times the opt plus a constant that depends on epsilon. And we can do this in polynomial time. The first observation is that, in a certain sense, small items, that is, items of size less than epsilon, do not matter. So we can assume without loss of generality that the items are ordered such that the largest items come first. Let's call the items of size less than epsilon small. Now the observation is that we can simply place these items last. So let's suppose we have placed all the items except an. Where can we possibly place an, the smallest item? So let's look at a configuration. So we have partially filled a number of bins. Now there are 2 cases for placing an. Either some bin has spare capacity epsilon, where an is small, this means that AN simply fits in one of the bins and the number of bins doesn't increase. The other case is that no bin has spare capacity epsilon. So we need a new bin. So we now have to create a new bin and place AN in it. Now I would like you to pause and think. Why do we still have a solution in this case that is close to the optimal in case 2, even though we have to add an extra bin? So using this reasoning, we can practically ignore all the small items and take care of them greedily in the end. So it basically suffices to solve the problem in the case where all the elements A1 through AN have length at least epsilon half. To solve the problem in the case where all items are large, we're going to do discretization via grouping. So consider all the elements here in sorted order. It could look something like this. What we're going to do is to group them into groups, each containing k elements. So we're going to define a new input that we can solve more easily and whose value or the solution to which actually gives us a good solution to the original problem. Okay, so the new input is basically a copy of the previous one, but in each group we round up the values to the maximum in the group. So A1, A2, A3 get a new value that's equal to A1. A4, 5, and 6 get a value that's equal to A4, and so forth. Also, we drop the largest group, so we simply throw these elements away. This gives us a new input I prime, and let's call the original input I. It's easy to see that by definition, I prime has only n over k distinct values. And this means that we can actually use the scheduling algorithm that we saw before. So using dynamic programming, when we only have a small number of distinct values, we can actually find a 1 plus epsilon approximation efficiently. We claim that the solution to I prime actually tells us something useful about the solution to I. So in particular, the solution to I prime has value that is less than or equal to opt, but it's not too far from opt of I. So it exceeds, or it's less than opt I by at most k. So let's argue for these two inequalities one by one. So for the first one, we want to argue that if we're given a solution to I, we can get a solution to I prime that has at most the same cost. So why is that? Well, the largest element in I prime is smaller than the largest element in I. Second largest is smaller than the second largest, and so on. So basically we can mirror any solution from I to I prime. For the second inequality, given a solution to I prime, we claim that we can get a solution to I with additional cost at most k. And this additional cost simply consists of putting the largest k items in one bin. Now we can do a mirroring similar to before. Why is that? Well, it's basically because the size or the vector of the remaining jobs is dominated by the vector of jobs in I prime. So it's easy to see that we can just maintain the same ordering of the elements in the item, and we get in the assignment, and we get a new valid solution that has the same number of bins apart from the k first. So finally, we choose k to be epsilon times the sum of all of the i's, which is at most epsilon times opt, and that gives us a solution that has the required value. Welcome to Approximation Algorithms. Today we're going to talk about linear programming and deterministic rounding. My name is Rasmus Pagh. The agenda is as follows. First, I'm going to give a quick overview or reminder of linear programming. Then we're going to look at our first case study, vertex cover, also mentioning set cover. We'll cover working with LPs in Python, and finally look at a case study, the price collecting standard tree problem. A linear program in its canonical form looks as follows. There's a number of decision variables, which are the ones we want to choose. Let's call them x1 through xn. So these are supposed to be real valued. We have a set of linear constraints of the form the sum of a linear combination of the xi should be bounded from above by a value bj, which is again a real number. And finally, there's a linear objective function, which is to maximize a linear combination of the xi. Let's look at a small example. In 2 dimensions, we can draw the set of feasible solutions to the linear program. We have the constraint that each variable should be non-negative, so the feasible region is in the upper right quadrant. And we can introduce constraints. 2x1 plus x2 is bounded from above by 1. And x1 plus 2x2 is bounded by above from 1. So this means that these grayed out areas are not feasible. So feasible region is in the bottom left corner. And we can also consider the objective function x1 plus x2, which means that the further up to the right we go, the better the solution is. So the optimal solution is going to be the one shown here. Of course, most of the time we are not going to work with 2-dimensional linear programs, but work in higher dimensions. But the intuition in the example carries over. So a feasible region is in general going to be an intersection of half spaces corresponding to the constraints. And an optimal solution can either be at a vertex, the intersection of n half spaces, in a corner if you like. In that case it's unique. It could also be along a face of the polytope, which means that there are many optimal solutions. Finally, it can be that the optimal solution doesn't exist, either because the feasible region is unbounded, or because there simply is no feasible solution. What we just saw was the so-called canonical form. In general, any linear program can be translated into a canonical form. A general linear program might have greater than or equal to or equality constraints. Maybe we want to minimize instead of maximize the objective function. And maybe we allow values that are less than 0. Okay. But it's always possible to translate this into an equivalent linear program in canonical form. So how do we do this? Well, I want you to consider the particular example here and think about how to translate these constraints into an equivalent linear program. And also think about how this carries over to the general case. Our first case study is the vertex cover problem. More specifically, we're going to look at the minimum weighted vertex cover problem. So we're looking at a graph with weights on each node and edges connecting the vertices. And the goal here is to select a subset of the vertices such that every edge can be oriented towards one of the selected vertices, or touches one of the selected vertices. Or in other words, we cover all the edges. In this case, the vertex cover that we have chosen consisting of 2 nodes with a total cost of 4. Okay, so formally we have an input graph and a weight function that maps vertices to real numbers. And we want to choose a subset of the vertices such that the sum of weights is as small as possible. And also it should satisfy the constraints that for every edge, either one endpoint or the other endpoint is an S, or they can both be there. Okay. So that's the problem. And here it's not obvious how to design a greedy algorithm. I'm not saying it's not possible, but there's an obvious way of formulating it as an integer linear program. Okay, so how do we do this? Well, we know what we want to minimize. It's a linear function. Let's define xv to be a 0,1 variable that indicates whether v is an s. Then we want to minimize the sum of weights multiplied by the variables xv. And then we have the constraints, which simply say that for nodes v, u, and v, we have to either have xu or xv equal to 1, or in other words, the sum should be greater than or equal to 1 for all edges. So note that because we require xv to be 0 or 1, this is not a linear program. So the integrality, of course, is hard to depict in high dimensions, but we can consider it in 2 dimensions where I think you can get some intuition. So let's look at the integer coordinates in 2 dimensions that satisfy some linear constraints. Okay, so maybe the linear constraints rule out these areas that are grayed out. Then, of course, there are some corners, some optimal values for the linear program, but the integer ones, are in general inside the polytope and not on the edges. So we want to know somehow, is there a way of going from the red optimal solutions to the LP to integer solutions inside the polytope. So in general, we can think about the LP without the integer constraint and try to convert an optimal solution to the LP, just allowing any value in the interval 0 to 1 instead of just 0 and 1, and try to convert it into an integer solution that is at least nearly as good as the optimal solution to the LP. Okay, and this method is called LP relaxation. And let's denote the optimal solution to the linear program by x star. So this is going to be a value in 0, 1 to the n if we have n variables. And we want to convert this into an integer solution x hat. Okay. And the idea is simple. We simply round. So if the LP has a value greater than 1/2, we round up to 1. Otherwise, we round down to 0. So now, why does this give us a good approximation? Well, let's look at the objective function on x hat. So it's simply the weighted sum of the variables x hat v over all v. And now, because the rounding cannot increase the value by more than a factor of 2, we can upper bound xv hat by 2 times xv star. And we can take the 2 outside of the sum. So then we have 2 times a weighted sum of xv star, and I claim that this is less than or equal to 2 times opt. Why is this? Well, the optimal solution satisfies all constraints that the relaxation does. And in addition, it satisfies integrality. So this means that the solution cannot be smaller than the solution to the LP. So this was an approximation, a 2 approximation for vertex cover. It can be generalized to set cover, and in fact that's what many textbooks do. So the set cover problem, there's a collection of sets, and you need to choose a sub-collection that covers all elements in the ground set. But please read the book to learn more about that. So next we are going to look at solving linear programs and vertex cover in Python. And I've made a small wrapper to the standard Python libraries for linear programming that is a little bit more user-friendly. And in order to use this, or one way of using this is using Colab, which is a hosted browser-based Python environment. And I've shared a link to you with you to this Colab that I'm showing you right now. That is solving vertex cover on some graphs. Okay, so the first thing you want to do is to just make a copy of the notebook so that you can edit it yourself. And then you want to connect it to a server that is able to run your code. So the code at the top here is simply fetching the wrapper that I made for the course. You can inspect the code here if you want to see how it works. But it's basically a wrapper around the SciPy libraries for linear programming. That is a little bit more user friendly and with fewer distractions, if you like. Okay, but I'm not going to go through that. So to solve a linear programming, we need to say whether we want to maximize or minimize. So we create an object that is either maximization or minimization linear program. And then we can start adding constraints. And there are two ways to add constraints. First, you can create a dictionary that gives a mapping from the variable names to the coefficients. And then finally, we want to give the upper bound. There's also a small parser that is able to parse at least simple constraints. And finally, we need to set the objective. And again, that can be supplied as a dictionary that gives the coefficients for each variable in the objective function. If you want to see the LP, we can convert it to a string. But more interestingly, we can solve it and get a solution out. Okay, so this is running the solver on this small LP, which was actually okay. So yeah, so this is printed out by the code that I talked about. There's also some more code about the dual of the LP, and we're going to get back to that in a later lecture. So for the vertex cover problem, we don't need duality. So let's look at the code for approximating vertex cover. So there's a class also called data file that is able to read simple graphs for you. So basically, we don't have to think about input-output. We just use that class. So we want a minimization linear program. And for each edge in the graph, we want to add a constraint saying that the sum of the two edges is at least 1. Since it's a minimization linear program, the standard constraint is greater than or equal to. And then finally, we want to ensure that each vertex get a coefficient of 1 in the objective function, because this is the unweighted vertex cover problem. Okay, so we after we have gone through all the edges, we set the objective function with all the vertices, and then we simply run the solver, and we get back a value and a solution, which is a dictionary that assigns a value to each variable. Okay, and we can run through the solution and output all the values and also round all the values. Okay, and here I've added a small number. This is to deal with rounding issues. If I didn't add that, it would mean that some numbers slightly less than 1/2 would not get rounded up to 1/2, and we would actually not get a valid solution because of numerical issues. But adding 10 to the minus 10 gives an almost true approximation, and it's kind of numerically stable. Okay, and now when this is run on a bunch of graphs. There's the karate club graph with friendships in a karate club. There are small graphs like clique and the Peterson graph, which is a famous example that's used. We have a graph over the characters in Lord of the Rings. So there's all kinds of graphs where we can try to look at so these are characters that meet each other in the Lord of the Rings books. Okay. And okay, this code simply runs runs the vertex cover approximation algorithm on all of these, and for each of them it outputs the optimal LP value, but also the value of the rounded solution. And we can see that for the routes graph, it's actually no better than a true approximation. So the LP gives a value of 5, and the rounded value has a value of 10. Okay, but sometimes there's a gap smaller than 2. Okay, so actually this gap is only a bound on the approximation factor. Okay, so it may not be the case that it's actually possible to find an integer solution or a rounded solution that is equivalent or as good as the LP solution. So the final case study today is the price collecting Steiner tree problem. And we will actually only get a partial solution today, but I'll come back to that. So what is this problem? Well, suppose that we have a graph with weights on edges, but also weights on the nodes. So think about this as maybe customers for a cable company that we think about connecting with fiber, and we have some route. Let's call it V star. So it says V right now, but we'll call it V star. And we have the option of creating cable along some of these edges in the graph. And this will impose a certain cost, which is simply the sum of the edge costs. So in this case, it will be 10. There might be some customers that are left out, unconnected vertices, and they are also going to impose a cost. That would be the profit, if you like, that we would get from connecting them. And the goal is simply to minimize the total cost. Okay. So the input in general is this graph with vertices and edges. And for each edge, we're going to get a cost let's call C, and for each vertex, a cost pi v. And the objective we can write in terms of decision variables. So let's define xe to be either 0 or 1, depending on whether e is in the tree, connecting v to a subset of the vertices. Okay, so it's important that the graph that we choose is a tree that connects v to a connected subset of the vertices. And then yv is 0 or 1, depending on whether v is in the tree or not. And the objective then is simply to minimize the weighted sum of the edge costs plus the weighted sum of the vertices that are not in the set. So that's the weighted sum multiplied by 1 minus yi. And this is of course a linear objective function. What is less obvious is whether there are linear constraints that can ensure that x and y are actually valid, that x includes a tree and that y is kind of consistent with the edges in the tree. So if we look at some set S and a vertex v in S, so let's in the example we have the set S consisting of 2 nodes, then we can observe that if yv is supposed to be 1, so if v is supposed to be connected to the root, then there must be some path from the root to v. And in particular, this means that there must be some edge that crosses the cut between S and v minus S that crosses this cut. Okay. So let's call all the edges that cross a cut between S and v minus S delta S. So then we can write a linear constraint that simply says that the sum over all edges in delta S of xe must be at least yi, or yv. So this ensures that if yv is 1, then there must be one edge that crosses this cut. And we require this for all subsets S and all vertices v that are in S. Okay. So now I'd like you to think for a while and argue that actually the converse is also true. If x and y are not valid integer solutions to the constraints, then there actually exists a constraint of the form that we just saw that is violated. Okay, so now we are ready to formulate the LP relaxation. So let's just rewrite the objective function and the set of constraints. So this was the objective function, and the constraints are as follows. So for each S subset of V minus V star, the root, and should also be non-empty, and each V in S, then we have the sum of XE over delta S is at least YV, and then also we want the root to be in the tree, and finally all the decision variables should be in the interval 0 to 1. So that's the LP relaxation that no longer requires the x's and the y's to be 0, 1, but just in the interval 0 to 1. So there are basically two kinds of decisions here. What value of y to choose and what value of x to choose. And we are only going to look at one of them today, so which is about choosing the vertices to connect, so choosing the values of y. And we're going to come back later to the so-called Steiner tree problem that chooses the edges in the tree. We're going to use, again, a rounding mechanism, which just simply says that if the LP relaxation has a value of at least 2/3, we're going to round up, otherwise we're going to round down. So we won't be able to do a full analysis now, but we can observe that at least the part of the cost function that has to do with the uncovered vertices is not going to grow too much. So let's look at that part of the objective function. So we are going to get this cost, sum over pi times 1 minus y hat. And we can upper bound that by 3 times the corresponding sum where we put the optimal solution of the linear program into that. And now the observation is simply that 1 minus y hat can be no bigger than 3 times 1 minus y star, because the worst case happens when 2/3 is rounded down to 0. So this suggests that we might be heading for a 3 approximation, and indeed that's also the case. However, there is an issue here that you might have noticed. So we are having an awful lot of constraints. For each S, and there's an exponential number of choices of S, we have one constraint. So what can we do? It seems impossible to get a polynomial time solution because just writing up the LP. What we can do using our knowledge of macro flow min cut is to determine in polynomial time if a constraint is violated, because this is simply we simply need to find a cut of value less than 1. So this gives us a so-called separation oracle. And let's talk about how one can solve LPs with a separation oracles. So the idea is that we don't start with all the constraints, or we could even start with no constraints whatsoever. And we can find a potential solution. And we can ask the oracle, is this a valid or feasible solution, or does it violate some constraint? Okay, so this is our potential point, and then the oracle might say, oh no, it violates this constraint, and we can go on like this, propose points, and the oracle will come back each time we don't have a feasible solution and give us a constraint that it violates. Okay, and each time we kind of add the constraint to the potential solution, and in order to find a new solution that satisfies all the constraints we know about, and we just repeat this. Okay, and the amazing thing is that there is a way of solving linear programming called the ellipsoid methods that only needs this kind of separation oracle. It doesn't need to know all the constraints up front. And if the separation oracle runs in polynomial time, then actually the whole LP method also can run in polynomial time. So it's only ever going to need a polynomial number of these constraints, even if there exists an exponential number of them. It should be said that this is not a practical method, the ellipsoid method, but sometimes it's used in practice to not state all the constraints up front, but state the constraints in a lazy fashion and only add constraints if it turns out that the solutions that you're getting out of the linear programming actually violate some of the constraints. Welcome to the lecture on approximation algorithms using random sampling and randomized rounding of LPs. My name is Rasmus Pagh. We're going to look at two case studies. First, weighted set cover, and then we are going to study weighted version of max set. We're going to see three different approaches: random assignment baseline, how this can be de-randomized, and a solution obtained by rounding linear programs. In the weighted set cover problem, we are given a collection of sets over some ground set. So let's consider these 6 sets and the elements inside of them. The objective is to find a subcollection, that is a subset of the set of sets, that covers all the points in the ground set. So for example, here we could choose 3 sets to form a subcollection, and we see that they include all of the points. And what we want to achieve is the minimum possible weight of all the selected sets. So the input includes the m sets and also corresponding weights w1 through wm. And the objective is to minimize a sum wi times xi, where xi indicates whether set number I is included in the subcollection or not. We also need a constraint to express that everything is covered. So to this end, we introduce notation bj. So bj is going to be the indices of the sets that cover element I. So for each I, we need the sum of these xi's to be at least 1. That means that I is covered. Okay, and of course xi should be either 0 or 1, because either we want to cover something or not. So that's the integer programming formulation, but we cannot solve that efficiently, so we relax it as usual to an LP formulation by just requiring xi to be in the interval 0 to 1. So the hope is that solving the LP will help us get a good solution to the original integer programming formulation. And again, we are going to be using rounding. So the deterministic rounding approach that we saw earlier would look as follows. So let's suppose we have an optimal solution to the LP x star. So then we need to round up to 1 if x star is big enough, and otherwise down to 0. So the question is, what is big enough? And it turns out that this really depends on how many sets can include an element. So let's define f as the maximum number of sets that include an element j, so the maximum of size of bj over j. And then it's not very hard to see, and the details are in the book, that if we round up whenever xi star is at least 1 over f, then we are going to get a valid solution, a valid set cover. So since we round up to a value that is at most f times larger than the LP solution, the worst rounding is intuitively that we round from exactly 1 over f up to 1. And this means that we are going to get an f times more expensive set cover compared to the LP, which is a lower bound on the optimal solution. So this is an f approximation. However, it's possible to do better if f is large. And one way of doing this is by using randomized rounding. So the idea now is that we don't choose whether to round up or down deterministically, but rather we round up and down with certain probabilities. Okay. And it turns out to be easiest to write the probability to round down. So a good choice here is to round down with probability 1 minus xi star to some power that is basically the logarithm of n. I've used 5 times the logarithm just as an example, but the constant here doesn't really matter that much. Okay, so now we have a randomized rounding approach. So the question is, what can we say about the properties? Would it actually work? So let's analyze the randomized rounding procedure for set cover. So this is how we round again. So there are basically two aspects to this. So first of all, do we actually get a valid covering? And in order to analyze this, it's relevant to look at the sum of these xi's. So it has to be at least 1, but if it's actually 0, then we fail, even if it's just for a single j. Okay, so what is the probability for a given j that this sum is 0? Well, by the choice of the randomized rounding procedure, it's the product over all I in bj that xi is equal to xi hat is equal to 0, and by definition this probability is 1 minus xi star to the power 5 log n, and we can put the parentheses like this. And now we are almost done, because we know that the sum of these xi stars is greater than or equal to 1. So this means that we can upper bound this by a number that's exponentially small in the 5 log n, and this gives us a polynomially small error probability. And the details are left to an exercise. Okay, of course this was just for a single j, so what's the probability that there exists a j such that this is the case? Well, we just sum all the probabilities. Basically, we upper bound the probability that such a j exists by the sum of the probabilities, and it's again less than 1 over a polynomial in n. Next, we need to consider the approximation factor. So what can we actually say about the weight of the chosen set cover? So sum of wi xi hat. But of course this is a random variable, so all we can hope to do is bound, say, the expectation. So let's try to analyze the expectation. So by linearity of expectation, we can write this as the sum of probabilities multiplied by wi. So this was linearity of expectation. And now we can use the expression that we have above for the probability that xi is equal to 1, and we can actually we can upper bound that by 5 log n times xi star. Okay, so that's pretty easy to see. And then yeah, just moving 5 log n outside, we get an upper bound of that times the value of the linear program, the optimal value of the linear program, which is again a lower bound on opt. So that is, we get an approximation factor of 5 log n. So this was just expected, but we can actually get this for sure if we just repeat this whole thing until we get, you know, something that is within a small factor of the LP lower bound. And by Markov's inequality, we are going to succeed with constant probability each time we try, so the expected number of attempts we need is going to be constant. So a small correction to the bound I wrote before. It can actually be replaced by 1 over e, which gives an even better bound. So let's turn to our second case study, which is the max set problem in a weighted version. So set has has an input that consists of clauses, of literals. So for example, this clause is satisfied if x3 or x7 is true, or if x13 is false. Okay. And in general, there are some number m of these clauses with any number of literals in each, and we have corresponding weights w1 through wn. So the goal is to choose values for the variables x1 through xn in order to maximize the weight of the satisfied clauses. So if we define yi to be 1 if and only if clause I is satisfied, it's the sum of wi times yi over all I. Okay, so a baseline solution, a really stupid one, is just assign all the values at random. And it turns out that this solution is actually not too bad. So okay, so let's use 0 for false and 1 for true from now on. So we just randomly assign either 0 or 1 to each of the variables. So what can we say about the weight we achieve? So the sum of wi times yi. So again, like before, this is a random variable, but we can analyze its expectation. So let's use linearity of expectation again. So we write it as a sum over all the clauses of the expected value of wi times yi. And since yi is an indicator random variable, this is just wi times the probability that yi is 1, or rather that is the probability that clause I is satisfied. So now this probability depends on the length of a clause, so the number of literals in a clause. So let's define li as the number of literals in clause I. Then it's easy to see that we kind of have L chances of satisfying clause I, and each of them succeeds with probability 1/2. So the probability of not satisfying is 2 to the minus li. So the probability of satisfying is 1 minus that. So the expectation is exactly the sum wi times 1 minus 2 to the minus li. And that is, since li is at least 1, this is at least half times the sum of the weights. And since the sum of the weights is an upper bound on opt, we have a half approximation. So very often these randomized rounding techniques can be de-randomized, and we're going to illustrate it here, showing how we would de-randomize the random choices that we just saw. So the goal, of course, is to get something at least as good as the expectation. So the idea is to look at something called conditional expectations. So conditional expectations are the expectations that you get by fixing a variable to some value. So we can look at the expected value of ei times yi conditioned on xi or x1, for example, being either 0 or 1. And it's easy to compute this expectation for a given formula, and we simply choose the value of x1 that maximizes the expectation. And then we repeat with x2, x3, and so forth. And the claim is that this doesn't decrease the expectation at all. Okay, so we are sure to choose x1 such that we get an expectation that is at least as big as the previous one. And to see this, simply write the expectation as the weighted sum of the expectation conditioned on x1 being 0 and 1. So the expectation is simply the average of these two conditional expectations, which means that one of them has to be at least as large. Next, we're going to see how to improve on this baseline using randomized rounding of linear programs. So let's define Pj to be the set of positive literals or variables in clause J, and Nj to be the set of negative variables in clause J. And also we are going to introduce some helper variables to express the integer program. So zi in 0, 1 will simply be the indicator variable saying whether clause J is satisfied. Okay. So we can write up an integer program now where we say that the goal is to maximize the weighted sum of satisfied clauses. So that's just wj zj. And we want to make sure that zj is consistent with the xi's. So in particular, this means that for every clause, there has to be at least one satisfied literal. And the number of satisfied literals can be written as the sum of the xi over pj plus 1 minus xi over the nj's. So this was the integer program, but of course we can relax it to a linear program, but by not requiring xi and zj to be integer, but instead be in the whole interval 0 to 1. So now these values we can interpret as probabilities. So zj can be interpreted as a probability that clause j is going to be true, and xi is going to be interpreted as a probability that we want to set xi equal to 1. So this suggests a randomized rounding algorithm in which we take an optimal solution to the linear program, so call that x star, and we set xi hat to be one with probability xi star. Okay. So the question is, does this work? Does it actually give us a solution that is comparable to the one in value to the one given by the linear programming? So to analyze this, we look at the probability that a clause is not satisfied, and by definition, the only way that you're not going to be satisfied is if all of the literals are not satisfied. So this is this product of probabilities. Now, to make this more manageable, we use the arithmetic geometric mean inequality, which says that we can basically replace all the things we are multiplying with their arithmetic mean, so the average, as long as we take that to the power, which is the number of terms. So this is the AG mean inequality. And now we basically just have the sum of all the xi stars and some of them negated. And by the linear constraint, we know that this sum is at most Lj minus Zj. So we can simplify the probability like this. So now this was the probability that clause J was not satisfied. So we need to reverse this when we compute the expected weight of a rounded solution. So this is what we are really interested in. So we are going to write this like before as the sum of weights times the probability that yi is 1. And well, we just bounded the probability that yi is 0. So we can use that to lower bound this probability as 1 minus the probability that is 0. And now we can use kind of standard inequalities to lower bound this expression as wj times 1 minus 1 over e. So that means that we have something that's at least 1 minus 1 over e times the LP optimum, which is again an upper bound on opt. Okay, and here we're using that set j star is less than or equal to 1. Even better algorithms exist, and you can read about those in the book. We're not going to cover them in the lecture. Welcome to Approximation Algorithms and the lecture on randomized rounding of semi-definite programs. My name is Rasmus Pagh. Today we are going to talk about convex optimization and how to use it for approximation algorithms. In particular, we're going to talk about semi-definite programming and how it's formulated as vector programming. We're going to look at two case studies. First, max cut, and we are also going to look at how to do that in Python. And we're going to look at correlation clustering. Linear programming, which we have used in the last few lectures, considers a collection of constraints that are all half-space constraints. So each constraint basically says that a feasible solution cannot be in a certain half-space. And we have a linear objective function which tells us the direction, so to speak, of the optimum. It is easy to see that if we look at this line segment between any feasible solution and the optimum solution, all those solutions are also going to be feasible. There's a much broader class of optimization problems that can be solved efficiently, as long as the constraints are convex, like in the case of linear programming. So in general, if we think about a collection of convex constraints, so they do not have to be linear, it's just that the set of points satisfying each constraint must be convex, and we need to satisfy all of these constraints. We are also going to have a convex feasible region. And if we have a linear objective function, then we have a property similar to the case of linear programming, where from any feasible solution we can walk in a straight line basically to an optimal solution. So linear programming is polynomial time solvable and also efficiently solvable in practice. For a general convex optimization problem, the picture is a bit more complex, but one could say that usually they are efficiently solvable, at least up to some additive error. So in the following, we're simply going to assume that we have a black box that can solve such problems. A particular kind of convex optimization is semidefinite programming, which we're going to define in the following. In semidefinite programming, decision variables form a symmetric matrix X that can also be written as a product of a matrix V transpose multiplied by the same matrix V. Here V is an n by n real matrix. The column vectors of V will denote by V1 through Vn. And this means that a particular entry xij in X is the dot product of the vector Vi with the vector Vj. And remember that the dot product is simply the sum of products of vector entries. The requirement that X equals V transpose V for some matrix V is often written X greater than 0. We sometimes say that X is positive semidefinite. Apart from the very different decision variables, a semidefinite program looks very much like a linear program. We have a linear objective function where we want to maximize a linear combination of all the decision variables. We also have linear constraints of the form that a linear combination of the decision variables must equal a particular value bk. So we have a collection of such constraints. And finally, as mentioned above, we need to constrain X to be positive semidefinite and symmetric. Often semidefinite programs are presented in a different form, also called vector programming. So here we use the entries of V directly as decision variables. So that is, we replace xij by the dot product of Vi and Vj, both in the objective function and in all the linear constraints. So that's the so-called vector programming form. As hinted at before, we can solve semidefinite programs at least approximately up to some small error in polynomial time. So we can use it as a black box for efficient algorithms. Our first case study for semidefinite programming is the max cut problem. The input is a complete graph where each edge has a weight wij, and the goal is to find a cut, a division into the vertices into a set S and a complement of S that maximizes the sum of the weights of edges crossing the cut. That is, the sum over all I in S and j in V minus S of Vij. Now it's time to pause and think. How can max cut, as we just defined, be formulated using vector programming, where we can require that the vectors have integer coefficients? Let us look at a vector programming formulation of the max cut objective. Suppose we have vectors Vi such that Vi dot Vj is equal to 1 if I and j are on the same side of the cut and 0 otherwise. Then we can write the objective function as the sum over ij of wij times 1 minus Vi dot Vj. Here we count Vij if and only if I and j are on different sides of the cut. And this is for all I less than j. What is the requirement on Vi? Well, we can fulfill it by making sure that all vectors Vi has plus or minus 1 in the first coordinate and zeros everywhere else. So here the sign of the first coordinate indicates whether or not the vector is an S, and the rest are just there as padding in order to get to n dimensions, which is required for semidefinite programming. Now, semidefinite programming doesn't allow us to restrict the coordinates to be integers. So we need to consider the relaxed version, where instead of requiring Vi to have the particular form written here, we relax it to requiring Vi to have unit vectors. That is, the dot product of vi with itself must be 1 for all I. Or in other words, the length of all the vectors vi must be 1. So the remaining question is, how do we go from these vectors, which are now general unit vectors in an n-dimensional space, to values in plus minus 1? We're going to look at this on the next slide. How do you round vectors in n dimensions to either plus 1 or minus 1? There are a couple of extreme cases that are instructive to consider. The first case is if v1 and v2 are almost the same vector. That is, the dot product is very close to 1, which is the maximum possible for unit vectors. This means that the contribution to the max cut is very close to 0. In this case, we want vertex 1 and 2 on the same side of the cut. So either both of them should be plus 1 or minus 1. The other extreme is where the two vectors are in opposite directions. So the dot product is close to minus 1, which is the smallest possible for unit vectors. In this case, the contribution to the objective function is close to the maximum possible of 2 times w12. We want these two vertices to be on different sides of the cut. And then, of course, in between, the middle case, if you like, is the situation where v1 and v2 are close to orthogonal. So the dot product is close to 0. In this case, the contribution to the objective function is going to be half of the maximum possible, so around w12. And in this case, it doesn't really matter. So we are happy if vertex 1 and 2 lands on different sides with probability 1/2. So this is the intuition. To implement this, or turn this into an actual rounding algorithm, we use a method now known as locality-sensitive hashing. In fact, this was invented exactly for the purpose of approximating max cut. So based on the intuition we had before, what we want is that the probability that the hash values of v1 and v2 is equal to each other is 0 if they have a dot product of minus 1. It must be 1 if they have a dot product of 1, and about 1/2 if they have a dot product of 0. And again, here we assume for simplicity that we have unit vectors. It turns out it doesn't really matter that much. Okay. So the idea of the construction is to sample a random hyperplane. So an n-1 dimensional plane that passes through the origin. And such a hyperplane can be described by a normal vector, r, that is orthogonal to all the points in the hyperplane. And then we simply map one side of the hyperplane to -1 and the other side to +1. So if v1 and v2 are almost in the same direction, then almost always the hyperplane is not going to split to divide them on different sides, but they are almost always going to end up either on the positive or the negative side. Whereas if they are in opposite directions, or almost in opposite directions, we are almost always going to get them on different sides of the hyperplane. In terms of the normal vector, this means that the dot product of the two vectors with r, the normal vector, is going to have a sign that can be used to say whether we are on one side or the other. Okay. And notice here that the sign is indeed independent of the length of the normal vector r. And the fact is that if we take r to be an n-dimensional normal distributed vector, it works. It gives us the normal vector of a random hyperplane. To analyze the approximation factor, it's instructive to look at the effect of the rounding. So here's the definition of the locality-sensitive hash function, also known as simhash. And we can plot the probability of hashing to the same value as a function of the dot product between two input vectors. So these are the three points that we wanted. So we wanted 0 collision probability if the dot product was -1, half at 0, and 1 at 1. So we could hope for the dotted line here. Unfortunately, that doesn't work, but what we can get is this green line. Please look at the book for details. So we have something that is pretty close to this ideal line, and is actually efficient, is actually possible, and you implement it exactly as described in the previous slide. To analyze the approximation factor, we need to compare the value of the objective function output by the semidefinite programming relaxation to the rounded value output by the locality sensitive hashing, which can be written like this. And well, basically you have to look at this particular curve for the expected value, and it turns out that it can be lower bounded by 0.878 times the objective value of the relaxed. And since the relaxed version is at least as good as the integer version, we have our approximation algorithm. Let's look at how this can be implemented in Python. So again, we are going to use the library that we used for linear programming, but here we are going to use only the data file class. The way this is implemented is a little bit more low level. You have to work directly with matrices. And in order to do this, we need a way of mapping between names of vertices in the graph and indexes in this matrix. So we are going to have two maps, one that maps a vertex ID, a string, to an index, and one that maps an index back to a vertex ID. So this checkVertex class here just registers new vertices and new indices like that. And we also have a class, graph weight matrix, that takes a graph as input and is able to insert all the edges of the graph into these two maps and output a matrix W that is all 0 except for indices that correspond to an edge. And for those indices, it contains a 1. And in this matrix, either for each pair u, v, either u, v is 1 or v, u is 1, but not both of them. Okay. So let's look at how this is used to solve maxcut, as we went through before. So we're going to solve the unweighted case on the graphs that we also looked at for LP-based randomized rounding. So, and we're going to use CVXPy, which is a library for convex optimization in Python. We're also going to use something called Cholesky decomposition from SciPy, from the SciPy library. So we have a loop that loops over all the graphs, and for each graph we read in the data and construct the weight matrix W. And n here is the dimension of this matrix. So to solve the semi-definite program, we define the decision variable x as an n by n symmetric matrix, and we define a constraint here that says that x has to be positive definite. Also, we add the constraints from the formulation that we saw just before, that xi, I, so that is the dot product of vi with itself, must be 1 for every I. So these are the constraints, and in order to define the problem, we call the constructor here, which takes two arguments. So the first argument here is the objective function, and it looks very much like what we saw in the lecture, except for this mysterious last part here. So let me just explain what goes on here. So we have the weight matrix, and we have a matrix that is the all ones matrix minus x, the solution. And the operator we have here is the so-called Hadamard product, which takes constructs a huge n squared by n squared matrix that contains all possible products of an entry of
W and an entry of 1's minus x. So this huge matrix contains everything we need to add up to formulate the constraint, or the objective function, sorry, in order to get out the right parts. So we want the weight ij to be multiplied by 1 minus xij. We apply the trace operator. So the trace operator does exactly that. So it picks out and sums exactly the entries where along the diagonal of this large Hadamard matrix, which is exactly those where the index of W matches the index of X. Okay. So this is just a reformulation of the objective function. And then the second argument is just the list of constraints. We can call solve to solve it, and now we can read off the optimal value as x.value. But in order to do the randomized rounding, we actually need the V matrix, not X. So we need to somehow recover V from X, and in order to do that, we can use something called Cholesky decomposition, which exactly takes X and writes it as a matrix product. So unfortunately, because of numerical issues, this doesn't work directly, because X is not exactly positive definite. So in order to deal with that, we can add the identity matrix scaled by some small factor, and this is enough to make the matrix positive semidefinite without changing it too much. Okay. So we're going to get a V out of this, which approximately is the square root of X, in the sense that V transpose V equals X. Okay. So now we have the solution in the right form, and we're ready to do randomized rounding. And in order to do this, so we're actually going to do this many times, 1,000 times in this example. In order to do this, we use the locality sensitive hash functions that we saw before. So we sample an n-dimensional normally distributed vector R, and we look at the dot product of R, which with each of the column vectors of V. And this gives us, and the sign, and compute the signs for each of these dot products. And this gives us the randomized rounding for each vector in V. And we can compute the cut here. So the cut are exactly those where the roundings, or the cut edges are exactly those where the rounding of U and V are different. So one rounds to -1 and one rounds to 1. And we can record the size of this cut. This is just the length of this list of cut edges. And we report over these 1,000 repetitions, we report the maximum cut weight found, and also the worst one, just for reference. Okay. So this is applied to all the graphs from before, and you can see here that we get the solution to the relaxed version here is pretty close actually to the best cut that is found. So the rounding works really well and is able to find a cut that has almost as good a value as the relaxation. And in fact, because we know that the optimal solution is integer, we can see that the optimum must be 13. Okay. In some cases there is a gap. So for example, if we go down here to the Karate Club. So the upper bound from the relaxation is 63.48. So we know that it's not possible to find a cut that's larger than that. So this means again that 63 is the best we could hope for, and the randomized rounding finds a cut of weight 61, so which is very, very close to the best we could imagine. It is important to do this a number of times. So we can be unlucky and find roundings that are considerably worse than what we would get in expectation. And that's pretty much it.
In the final part of the lecture, we're going to look at a correlation clustering problem. The input consists of two matrices. So W plus and W minus, and the entries are subscripted with I and J. Both are n by n matrices. And so think about these as two different weightings on complete graphs, and the output must be a mapping into clusters. So each vertex V is mapped to a cluster C of V for each index up to between 1 and n. And the objective is to maximize the sum of Wij plus over all things in the same cluster plus the sum of Wij minus over all things that are in different clusters. So think about all the indices as points. In this case we have we have split them into 5 different clusters. So for every pair of points or vertices in the same cluster we gain Wij plus, and for every pair of vertices in different clusters we gain Wij minus. Okay, so now I would like you to pause and think. How can we express or formulate correlation clustering as a vector programming problem? And a hint here is that we want the decision variables, the Vi and Vj's, to satisfy that the dot product is 1 if and only if I and j are in the same cluster, and 0 otherwise. Let's look at a vector programming formulation of the correlation clustering problem. So the objective from before is like this, and we want to express the decision variables as dot products such that Vi, Vj is 1 for those pairs in the same cluster and 0 otherwise, and this means that our objective function should look like this. Now we have a 1 here, which is kind of different from the form that we said that vector programming could have, but this is just basically a constant that is the same, so it doesn't change the optimal. And now one way of achieving this is to require that each Vi is a basis vector, standard basis vector. Of course, we cannot really know if we get standard basis vectors out of a solution to semidefinite program. So, but what we can require is that we get unit vectors out. And furthermore, we can require that we get non-negative dot products. So all the dot products must be at least 0. So this is the relaxed semidefinite programming formulation. And the next step, of course, is that we need to map these unit vectors back into clusters. So for each vector V, we need a cluster C of V. And ideally, what we would like to do is to kind of mimic the objective function and get that the probability of mapping to the same cluster would be exactly the dot product of Vi and Vj. And of course, this means that the probability of mapping to different clusters would be 1 minus that, and that would give us exactly the right expected value. Unfortunately, as we saw before, it's not really possible to achieve this, but we can get pretty close with this sim hash locality sensitive hash function. So indeed, this is what we're going to do. So the actual random clustering that we do uses not 1 but 2 of the sim hash functions, so h1 and h2 chosen independently, and we define the cluster of a vertex V as the concatenation of the sim hash values. So we get a vector of length 2 with entries in -1 plus 1, so four distinct clusters. And now we know the collision probability of sim hash and its relationship to the dot product. So we can show that we can bound the expected value of the objective function by 3/3 times the value of the relaxed version, which again upper bounds opt. Welcome to Approximation Algorithms and the lecture on the primal dual method. My name is Rasmus Pagh. We'll start today with a recap of linear programming and some intuition. Then we are going to discuss the primal dual method through 3 case studies: shortest path, feedback vertex sets, and Steiner tree. Linear programming duality can be seen as a way of showing upper bounds on the optimal solution of a linear program. We do this by solving another different optimization problem, which is also an LP. Let's look at an example. We have decision variables x1, x2 confined to the interval 0 to 1, and we have 2 linear constraints. The objective is to maximize the sum of x1 and x2. What can we say about the optimum solution? So one simple observation is that x1 and x2 are both bounded by 1, so the sum is bounded by 2. Here we have combined 2 of the constraints into an upper bound on the optimal solution. But there are many ways we can combine constraints. We can take linear combinations of constraints. For example, we can multiply the first constraint by 1 over 7 and the second constraint by 3 over 7 and get 2 other constraints that, when we add them together, imply that x1 plus x2 is bounded by 5 over 7. Let's look at this graphically. So this is the plane of all possible values for x1 and x2. And we can draw the constraints. So these are the constraints saying that these values are less than 1. And the intersection of these 2 constraints correspond to the optimum value of 2, or the upper bound of 2 that we just discussed. The next 2 constraints are drawn like this, and their intersection is the point marked in yellow here. So this intersection is the place where these 2 constraints hold with equality. And the value of the objective function in this intersection is exactly 5 over 7. So in general, at the optimum, we are going to have a set of tight constraints that hold with equality, and these are going to imply a bound on the maximum value. Let's look at duality in general, and for simplicity we are going to focus on the standard form of LPs, where we want to maximize the dot product of a vector c and a decision variable of vector x under a constraint that ax is less than or equal to b. Here we're using matrix notation. Here c and x are n-dimensional vectors. A is an m by n matrix, and b is a vector of m constraints. The dual becomes a minimization problem. We want to minimize bt times y, where y are some new variables corresponding to the constraints in the original linear program, under the constraint that A transpose times y is greater than or equal to c. So here b, a, and c are as before, and y, the new decision variables, belongs to Rm. These 2 linear programs are related in various ways. We have the weak duality principle, which says that for a feasible x and feasible y with respect to the dual, we always have that the value of the objective function for the primal is bounded by the objective value of the dual. Second, we have the strong duality principle, which says that if both the LP and the dual have a feasible solution, then in particular they have optimal solutions, and they have the same value of the objective function, that is c transpose x star equals b transpose y star, where x star and y star are the optimal solutions. Finally, we have the so-called complementary slackness conditions, which give a sufficient condition on a dual and a primal feasible solution to be optimal. The first condition says that if a primal variable is greater than 0, then the corresponding constraint in the dual is tight, holds with equality. And symmetrically, if a dual decision variable is positive, then the corresponding primary constraint holds with equality. If those two conditions hold, then the complementary slackness condition says that x and y are both optimal. We won't be using the complementary slackness conditions directly, since we are mostly interested in integer solutions, but we can use the same idea of going back and forth between primal and dual solutions. The typical game plan is to take a primal infeasible x and a dual feasible y and start improving it in the sense that we find ways of improving the objective value of a dual. This means that we increase some yi such that a constraint becomes tight, corresponding to some decision variable xj. Then we are going to use this as a clue as to how to change the primal. So that is, we are going to modify xj. And this process is repeated until we arrive at a feasible x. When analyzing the value of the objective function for the solution that we arrive at in this way, we can use the fact that all the constraints that we applied are tight. Let's make this more concrete by looking at a few examples. We're going to start by looking at a problem that you all know. It's an optimization problem that is actually in polynomial time. So we're going to be aiming for an exact solution. So the input is a graph, v, e, and let's say it's undirected, and for each edge we have a weight ce that is non-negative. There's a designated start vertex s, and we want to output a shortest path tree with root s. So the output is going to look something like this, and for a given node t, we can find the shortest path, or a shortest path from s to t, by following the edges in the tree that lead from s to t. Dijkstra's algorithm is the most famous algorithm for solving this problem, and it works by gradually growing the shortest path tree. So there's some current tree, and we look at possible edges to add to the tree. The one that is chosen by Dijkstra's algorithm is the one that minimizes the path length from s. So that is the edge that leads to the node that is closest to s among all the nodes that have not been explored. We can formulate this problem as an integer program. So let's introduce a decision variable xe that encodes whether an edge e is in the tree. Then we want to minimize the sum of all weights of chosen weights, subject to constraints that basically say that we want to connect all vertices. And this is expressed by saying that for every cut s, v minus s, if we sum over all the edges that cross the cut, delta s, the decision variable xe, then it has to be at least one. So at least one edge has to cross the cut. And this is not hard to see that if we constrain xe to be 0 or 1, then this is equivalent to the original shortest path problem. Let us write up the dual linear program. So the primal is here. In the dual linear program, we're going to maximize the sum of decision variables ys, where ys corresponds to the constraint s in the primal program, linear program. Also for each decision variable xe, we are going to have a constraint that says that if we sum up the ys for all the cuts s that where e crosses the cut, then this has to be bounded by ce. So this is the dual LP. So let's look at a step of the primal dual algorithm. So we are going to have selected some set of vertices making up a tree, f, and there's going to be some nodes like this one t that are outside of this tree. So since we don't have a spanning tree, some constraints are going to be violated, and in particular if we look at this tree which has a vertex at C, if we sum all the decision variables corresponding to edges crossing this cut, they're going to sum up to 0, which means that the constraint is not satisfied. And we're going to maintain the invariant that this means that the yc, the corresponding decision variables in the dual, is 0. This means that we can increase yc in the dual solution until the sum constraint is tight. So let's say that the tight constraints correspond to an edge CE, then we simply add the edge E to the shortest path tree. Now, it turns out that if you do this, the edge you add is going to be exactly the same as in Dijkstra. So I want you to pause and think and answer the question, why is that? Now we're going to go back to optimization problems. The feedback vertex set problem is a problem on an undirected graph with weights, and the objective is to remove nodes from the graph. So we have weights not on the edges but on the nodes, and we want to remove a subset of the nodes and adjacent edges such that when we remove these nodes, the remaining graph is going to be acyclic. And we want to do this in such a way that the sum of the weights of the nodes we remove is as small as possible. And weights are non-negative. So we can write this as an integer program. Again, we make a decision variable for each choice we have to make. So xi indicates whether node I is removed or not. So we want to minimize the weighted sum of these xi's. And we have a set of constraints that says that for each cycle we need to remove at least one node. So the sum of xi over all I in the cycle should be at least 1. And if we require xi to be either 0 or 1, this is equivalent to the feedback vertex set problem. Since the primal is a minimization problem, the dual is going to be a maximization problem. So there's a typo here on the slide, where we aim to maximize the sum of the decision variables yc, subject to constraints corresponding to the decision variables in the primal. So for each I, we want the sum of the yc's containing I to be bounded by wi. Both of these linear programs are kind of impractical. One has a huge number of constraints, the other one has a small number of constraints, but each of them has a lot of terms. But these are just going to be tools for analysis, and we're not ever going to actually construct them. In the primal dual algorithm, we start with x equals to 0 and y equals to 0. So x equals to 0 is not a feasible solution in general, if we have any cycles, and y is going to be feasible in the dual. So now we look for a violation of the constraints of the primal. So we are going to look for a cycle where none of the vertices have been selected, and we are going to try to find a particular one C that has the smallest number of degree 3 or more vertices. Okay, so degree 1 or 2 we are going to ignore. So that gives us a cycle C. We can find it using breadth first search, and we are going to increase the corresponding dual variable yc until there's some constraint in the dual that becomes tight and holds with equality. So this means that there's going to be some vertex I such that this sum of yc for all cycles C that contain I is going to be equal to wi. So this is a tight constraint in the dual setting. And then we are simply going to set xi equal to 1. So include vertex I in the solution. And we're going to repeat this over and over again until there are no cycles left. Okay, and each time we add I, it's kind of removed from consideration, from the set of cycles that we consider. Okay. So in order to analyze this, we look at the cost of the solution. So that's just the weighted sum of these xi's. And now we can use the fact that each wi that has xi equal to 1 is equal to a sum of the dual variables yc for cycles c that contain I. So if we can upper bound this sum by some factor f times the sum of yc's, then we're going to get an f approximation. So in the next slide, we're going to consider this. So let's start with what we had before. So we can see that each yc appears some number of times, and we can express this in terms of a sum over all the cycles, where we weigh each yc by the number of cycles it appears in. So if S is the set of vertices in the solution, S intersection C is going to give us the number of times that yc appears. So let's look at an example. So suppose the graph looks something like this. We're going to have some paths in the graph that have only degree 2 vertices. So for example, up in the top here we have a bunch of degree 2 vertices, and it's clear that once we choose one of these for the primal solution, then we're never going to choose another one of these again, because they're never going to be on a cycle again. Okay. On the other hand, for higher degree vertices, it can be the case that we choose several vertices on a cycle. But it's always possible to find a cycle that has fewer of these high degree vertices of degree at least 3. So I claim that we can always find a cycle with at most a logarithmic number of these, not counting the degree 2 vertices. And this can easily be seen by looking at the BFS tree, where the number of vertices grows exponentially with the depth of the tree until a cycle is found. So by carefully choosing the cycle C, we can upper bound S intersection C by a logarithmic factor. So we get log n times the sum of the yc's, which again is upper bounded by opt. The logarithmic factor is not the best possible. In section 14.2 of the book, you can read about a 2 approximation, also based on a primal dual algorithm. The next example we're going to consider is the so-called Steiner tree problem, which is a generalization of the minimum weight spanning tree problem. Like for minimum weight spanning tree, we have an unweighted, undirected graph. Furthermore, we have a subset of the vertices that we care about connecting. So let's denote this subset by T, since these are also called terminal vertices. Okay. So the task is to find a tree that connects all the vertices in T while minimizing the weight. Vertices that are not in T may or may not be in the tree. So in this example, for example, we could choose these three edges perhaps, and we would have a tree that connects all the terminal vertices. We can formulate this problem as an integer program. Again, we make a decision variable for each edge, and we want to minimize the weighted sum of the xe, where we use ce to denote the weight of he. We want to express that all terminal nodes need to be connected, and we can do this similar to what we have seen before in terms of cuts. So we are going to require that the sum of all edges that cross a cut, delta s, is at least 1 for all cuts that separate terminal vertices. So that is all cuts where that includes some, but not all of the terminals. So let's denote this set of cuts by p. So I'd like you to pause and think. Why is this problem equivalent to the Steiner tree problem? So this is our primal LP, and we can consider a relaxation where we scrap the constraint that x is 0 or 1 and instead just require that x is greater than or equal to 0. We could say less than or equal to 1 as well, but it doesn't have any effect on the optimum, since we are minimizing a sum of positive weights. So the dual LP then becomes a maximization problem. Again, all the constraints in the primal have a 1 in them, so we just maximize the sum of ys, and we're going to have a dual constraint for each variable in the primal, saying that the sum of all the cuts that involve a particular edge e must be bounded by the weight of edge e. In the primal dual algorithm, we are going to start with an infeasible primal solution where we have no edges at all. So here we have connected components that have each of the terminal vertices isolated. So let's call these C1, C through C2, and so forth. And each of them correspond to a constraint that is violated in the LP. Now we are going to increase all of the decision variables corresponding to violated constraints, or these violated constraints, until there's some constraint that is satisfied with equality. So let's say that this constraint corresponds to variable e. Then we are going to add e, the edge e, to the primal solution. Okay, and this is always going to be contributing or connecting to one of the components. It might even connect two of them. Okay, so this means that this component is going to grow, and now we have a new set of connected components, and we have a new set of primal variables to increase, and we go on like this, adding edges that become tight one at a time, until we have a tree that connects all of the terminal vertices. And this can never create a cycle, because we always add an edge that crosses the cut. Finally, we want to remove any dangling edges that don't contribute to connecting terminal vertices. To analyze the weight of the tree that we arrive at in this way, we again use the equality that CE, weight for an added edge, is equal to the sum of the ys for all cuts that are crossed by the edge e. So now the contribution of ys can be bounded by the number of times that an edge is in such a cut. We would like to upper bound this by 2 times the sum of the ys's, which would imply a 2 approximation. However, it's not true that edges from a particular cut are added at most twice to the solution. What is possible is to show the inequality by induction on the size of the tree f. Please see the book for details. In the book, they consider a more general problem called the Steiner-Forest problem, where we have several pairs of vertices S1, T1, S2, T2, and so on, that all need to be connected pairwise. For the Steiner tree problem, there is a better approximation algorithm known. Now, the best current approximation factor is approximately 1.38, or logarithm of 4, by BARC et al. Welcome to Approximation Algorithms and the lecture on multi-way cuts and hardness of approximation. My name is Rasmus Pagh. Today we have two independent parts. First, I'm going to talk about multi-way cuts. We are going to see a 2 approximation by repeated cuts and a 3/2 approximation using randomized rounding. In the second part, we are going to look at hardness of approximation results. First, we're going to see reductions from NP-hard problems, and then we are going to have a look at fine-grained reductions. The K-way cut problem is defined on an undirected weighted graph with non-negative weights. There are k distinguished vertices named S1 through Sk, and the goal is to remove edges that disconnect these vertices from each other. So in other words, S1 through Sk need to be in different connected components after removing these edges. We want to minimize the weight of the removed edges. In the example, we could remove these 5 edges and the 3 distinguished vertices would be disconnected. Suppose that f star is an optimal solution to the K-way cut problem. That is, it separates S1 through Sk. Look at the corresponding connected component for each distinguished vertex. Obviously, each edge of f star has at most 2 vertices, so it can touch at most 2 components. Also, the edges of f star that touch a particular component Ci is a cut between Si and the other distinguished vertices. This suggests the following algorithm. So for I equal 1 to k, we compute a min cut, fi star, that separates Si from the other distinguished vertices. This can be done in polynomial time. And finally, we output the union of all the cuts. I would like you to pause and think. Why does this give an algorithm that is a 2 approximation to the optimum? To get a better approximation, we consider an integer programming formulation that we are going to address via LP rounding. In this formulation, we introduce decision variables xui that indicate whether a vertex u is part of the connected component Ci, where Si is present. Obviously, at most one of these can be set to 1. The objective is to minimize the sum of all the weights of edges that have endpoints in different components. We need to somehow formulate this as a linear objective function. The first try would be to say that this is simply the L1 difference between xu and xv, where xu is the k-dimensional vector indicating where u is present. The L1 distance is simply defined as a sum of absolute differences between the components. It's 1 if and only if they are in different components. In order to write this as a linear constraint, we use a trick you have also seen in the handouts, which is to introduce an auxiliary variable that is larger than or equal to both xui minus xvi and minus that. Okay? So this is going to have an optimal value, which is the absolute value. So we can simply replace the objective function by the sum over Ci multiplied by this auxiliary variable zei. So how do we round this? So we are going to end up with some vectors that make up an optimal linear programming formulation solution. And the vectors corresponding to the distinguished vertices must be standard basis vectors, because the ith coordinate is 1 and the sum of all coordinates is also 1. So intuitively what we want to do is, if u has a corresponding vector xu, we want to put u in the connected component where xu is close to the vector xsi. Simply assigning each vertex to the closest standard basis vector turns out not to work. Instead, we are going to do a stepwise greedy algorithm that starts by randomly shuffling the order of the distinguished vertices. So now assume that S1 through Sk are in a random order compared to the input order. Now we're going to pick a threshold R in 0, 1 at random, and we are going to iterate through the distinguished vertices in the random order. So if there's a vertex that is unassigned and it is close to the ith standard basis vector, we are going to put it into component 1. And here close means that the ith component is more than 1 minus r. So it's within distance r on the ith component. And then finally, in the kth iteration, we will put all the unassigned vertices in component k. So this is how we define the components, and finally we return the set of edges with endpoints in different components. So we're going to get a component for each distinguished vertex, and there are some edges crossing it, and that's our solution. So let's look at a vector xu. So it's a vector where the sum of all the entries is 1. And yeah, the ith component is xui. So if we draw the threshold 1 minus r here, we are going to assign u to the index I, that is the first one to cross or be above the threshold 1 minus r, or if no such index exists, it's going to end up in component k. In order to analyze the randomized rounding algorithm, we write the expected cut value in the usual way as the sum over all edges of the weight times the probability that this edge is cut. Now I'm going to claim that this probability can be upper bounded by 3/4 of the L1 distance between xu and xv for an edge u to v. So if we take this for granted, we are done. Why is that? Well, the L1 distance can be written in terms of the objective function of the linear program that we saw before, which again is a lower bound on the optimal value of the integer program. Let's look at how to analyze the probability that u and v are in the cut. So to that end, we consider the corresponding vectors xu and xv. And we can draw kind of the histogram of the k values. Let's define index L as the index with the largest value looking at both xu and xv. So there are no values above that. If 1 minus r is between the value of xu and xv on some coordinate, it may be that v is placed in the corresponding component, but u is not, or vice versa. It may also be the case that 1 minus r is smaller than both u and v. So in this case, for example, both u and v are placed in C1, since they both exceed 1 minus r in the first component. Finally, it may be that 1 minus r is above everything. Then both u and v end up in the kth component, and there is no cut. An important observation is that it's impossible that u and v are still not placed after visiting index number L, and that one of them is placed at an index there, but not the other one. This is simply because if 1 minus r is less than or equal to one of the components, it would have been placed already at step number L. So those indices that are after L can never cause a cut between u and v. So when we choose or try to prove the claim, we only need to consider the cuts that happen, so to speak, before L or at L. And we notice that we can only get into the cut if 1 minus r is in this interval between xui and xvi for some I. And this has probability over the choice of r, that is the absolute value between the difference of xui and xvi. Also in expectation, half of the i's are going to be before L because we have a random permutation. So these are the main ingredients of the claim. Please see the book for details. And now for something completely different, hardness of approximation. In a usual NP hardness proof, we take an instance of some NP hard problem, let's call it P, and we translate it in polynomial time to an instance I prime of a target problem P prime, such that answers to P prime corresponds to answers to P. This means that P prime must also be NP hard. Hardness of approximation proofs can be constructed in a similar way. We start with an instance of an NP hard problem P, and in a poly time reduction we translate it to an instance of an approximation problem P prime, such that for some threshold T and for some approximation factor alpha, we have that if the answer to the original problem is yes, the answer to the P prime is less than T, and otherwise it's more than alpha times T. This is for minimization problems. So that is, we have a gap of a factor of alpha between the yes and the no instances. This means it must be NP hard to approximate P prime within a factor better than alpha. Of course, the similar thing works for minimization problems. Let's look at some examples. The case-center problem that we looked at before and derived a true approximation algorithm, we would like to show hardness. We're going to start with an instance of dominating set. So the dominating set problem takes a graph, v, e, and asks if there exists a dominating set. So that's a subset of the vertices of some size k, which is an input, such that the vertices of S contain a neighbor for every vertex in the set V. So for every V in V, there must be an adjacent vertex in S. So we reduce this to the case-center problem by defining a distance function that is 1 if U and V are in the edge set and 2 otherwise. So we observe that this defines a metric. Now the dominating set of size k, if there such a thing exists, implies a case-center of radius 1, because everything will be within distance 1 of one of the centers. And vice versa, if we have a case-center of radius 1, that corresponds exactly to a dominating set in the original problem. Of course, if the radius is 1, by definition of the distance function, if distance 1 is not possible, it must be 2. So in other words, if we could at 1.99 approximate case-center, we would be able to distinguish between the case where a case-center of radius 1 and 2 exists, and hence a 1.99 approximation must be NP hard to achieve. Next, we're going to look at the traveling salesperson problem, where we derived a 1.5 approximation for the metric case. We're going to show a hardness result for the general case, where we don't have a metric. We'll start with an instance of the Hamilton path problem, which asks if there exists a closed cycle connecting all vertices and does not visit a vertex twice. This is an NP hard problem. To reduce this to an instance of traveling salesman, we define a distance function that is 1 for every edge in the set and very large, let's say 2 to the n otherwise. So 2 to the n here is chosen simply to be an n-bit number we can write in linear time. So remember that the reduction has to be polynomial time. Now there exists a Hamilton cycle if and only if there is a TSP tour of length n. If there's no TSP tour of length n, the shortest possible length must use one of these long edges and have length at least 2 to the n. This means that approximating TSP up to a factor of 2 to the n over n is NP hard. Here the factor 2 to the n is a little bit arbitrary. We could increase it to 2 to any polynomial in n. Next we look at bin packing. For bin packing we saw something that was almost an approximation scheme but had an additive error. Let's show a hardness of approximation for pure approximation. So we start with an instance of the partition problem, in which we are given n integers and ask if it's possible to split the integers into two parts, where s is in one part, such that both parts contain exactly half of the sum. So in other words, the sum over all bi in s must be half of the sum b. This is known NP-hard problem. We can reduce it to bin packing by scaling ai to be 2 over b times bi. Now it's easy to see that we can pack these modified numbers into two bins of capacity 1 if and only if the answer to the partition problem is yes. Of course, if it's not possible to pack into two bins, we must need 3 or more bins. So this means that if we could approximate bin packing within a factor of 4.999, we could solve the partition problem. So hence this problem must be NP-hard. Finally, I want to mention some famous inapproximability results that we won't have time to show. The first one is for the max E3-SAT problem, where we have a 3-SAT instance and we want to approximate the number of clauses that can be satisfied. We saw that a random assignment satisfies a fraction 7 over 8 of all the clauses. Turns out that we cannot improve this even with a small epsilon larger than 0. There's a deep proof about this that goes via the so-called PGP theorem. There are also known inapproximability results for max cut. Unless p is equal to np, it's known that max cut cannot be approximated within a factor of 16 over 17, which is not so far from the approximation factor that we saw using randomized rounding of 0.878. Also, this approximation factor, the upper bound, is known to be the best possible assuming that the so-called unique games problem is hard. Unique games is a famous problem neither known to be NP or NP-hard. It's connected to a lot of approximation problems. Finally, we are going to look at so-called fine-grained hardness results, which are not covered in the book because these are recent developments. But the idea here is to show hardness also for problems that are not NP-hard but are in polynomial time. So many of the fine-grained results start with the so-called strong exponential time hypothesis, which says that the satisfiability problem requires time 1.999 to the power n, where n is the number of variables in the SAT instance. And here 2 to the n is the time bound for the best known but also the trivial algorithm for satisfiability that just tries all combinations. A related problem is the orthogonal vectors problem. So we're given two sets of size n of vectors of log n dimensions, binary vectors, and we need to determine if there exists a vector in pair x in A and y in B that have a dot product of 0. So that is, they don't share a 1 in any of the log n dimensions. There's a trivial quadratic time algorithm that just tries all pairs, and it's known that an algorithm that is faster than that, so that runs in time O of n to the 1.999 would imply that the strong exponential time hypothesis is false. So in other words, assuming the strong exponential time hypothesis, it isn't possible to achieve such an algorithm for the orthogonal vectors problem. Now we're going to see an example of a fine-grained approximation hardness result. So we are going to assume that the orthogonal vectors problem is hard and show that this implies hardness of an approximation problem. So we start with the instance with sets A and B of the orthogonal vectors problem, and we want to create an instance of the so-called L infinity closest pair problem, which is what we'll show hardness for. So this is given two d-dimensional vectors, x and y. And we want to ask what is the minimum distance between a vector in x and a vector in y, where we measure distance in terms of the L-infinity distance, which is simply defined as the maximum coordinate-wise distance. The reduction goes as follows. So we're going to create the set x from the set A from the OVP problem. For each vector A in A, we're going to define x A, where the ith coordinate is either 1 if AI is equal to 1, or 1/3 if AI is equal to 0. And the set y is defined from B in almost the same way. If BI is 1, we set it to 0, otherwise we set it to 2/3. It's easy to confirm that the L-infinity distance between XA and YB is either going to be 1, and this happens if there is a coordinate that where both AI and BI is 1. So in other words, if the dot product is greater than 0, otherwise it's going to be 1/3. So if there exists a pair with a dot product of 0, they have L-infinity distance 1/3, otherwise all pairs have distance 1. That means that solving the closest pair problem within approximation factor, say 2.99, in time n to the 1.999 would imply solving the orthogonal vector problem in the same time bound.